Hi guys, hope you can hear me, everyone.
Yes, sir.
Write a heading, thermodynamics. So what is thermodynamics, guys? Any idea? It is basically the thermodynamics is the study of energy, work and heat and the transformations between energy to work and work to heat. Okay, so you write thermodynamics is the study of energy, work and heat and the transformation between these quantities. Between these quantities. Okay. So where we use thermodynamics? Almost everywhere, right? In our body is also one of the most complex thermodynamic system. So basically we use thermodynamics in power generation. Okay. Example of that would be fossil fuel power plants or internal combustion engines or gas turbine engines or solar thermal power plants. Okay. Fine. And it is also thermodynamics is also used in high speed flows. High speed flows of especially gases. That is, thermodynamics is highly useful in study of compressible flows. Examples of that would be jet engines, rockets, high speed aircrafts, spacecrafts. Okay. Then the other uses could be heating, any sort of heating we require. Then ventilation and air conditioning. Okay. Refrigeration. The other usage could be combustion or you're dealing with phase changes. Hope you all noted till here, everybody. Fine.
Yes.
Can I go? Right. A closed system, you write. A closed system. So when we say a closed system, the meaning is you are having the control mass. Okay. For example, let me take an example. Just a second. Let me take this kind of typical example for you. So what is it? I am able to move this particular piston by a distance in or out. Okay, fine. I can do a work on the system, or if I have very high pressure gas, I can get the work done by this system also. Okay, so let's say this is This one is a simple. Imagine I am working on this fluid. Fine. So what is happening? I can supply the heat to it into the system, or I can extract heat from this system. But there is no exchange of mass. There is no mass transfer. Okay. Such a system in which you can do work, you can have the heat transfer and work transfer, but there is no mass transfer. Okay. So it can be anything actually. I'm just showing you one. But a closed system is a quantity of matter chosen for your study, which is not having exchange of mass out of the boundaries. Okay. So you write a closed system. A closed system is a particular quantity of matter chosen for study. Chosen for study. The system may change shape and location, but it is always the same matter. Always the same matter. So what number of particles are available? Same number of particles are available, whatever you do in the whole process. So that is called closed systems are called as control mass systems also. Write a heading, surroundings. So everything else other than the system is called surroundings. So something which is not the system is called surroundings. So you write the surroundings consist of everything that is not the system. That is not the system. And which has an effect on the system. Okay. So I will not be considering the surroundings of my room or my particular control region on which I am doing study. Okay. As some other, suppose I am conducting a small experiment in my laboratory, I will not take the surroundings as the other country or other city. I'll take the surroundings as some region which is having an effect on my system. For example, the surrounding ambient pressure or temperature will have an effect on the system. So that I'll take as the surrounding. Okay, you write next, boundary. Write a heading, boundary. So there can be moving boundaries also, there can be fixed boundaries also. And there can be real boundaries also, there can be imaginary boundary also. So a very simple definition of the boundary is the boundary of a system is the surface separating the system and surroundings. System and surroundings. For example, the case that we took here, if I take this case, okay, if I take this, what kind of boundary do I have here? What is this boundary, guys?
A real boundary, sir. Real bound.
All these are real boundaries. Okay. So in this one, what is this boundary? It is a moving boundary, right? It is a moving boundary, right? Now, suppose I take another case. I'll take a case like this. Let me take this case. Now, if this is the system that I have, in this one, what can you say about this boundary? This one and this one. This is a real boundary. This one is a real boundary. But is this a real boundary? This one and this one? Inlet and outlet? What are those boundaries? They are the imaginary boundaries. Okay. So this is imaginary boundary. This one is also an imaginary boundary. Note that. Surface. When you wrote surface, right? You write here, it could be real surface or it could be imaginary surface. That need not be really the surface, solid surface at all. Okay. Hope you noted that, everybody.
Yes, sir.
So we are going to do the aircraft propulsion as if you don't know anything in aircraft propulsion. Okay. So you write isolated system. Isolated system. So imagine if I consider some sort of a container like this, in which I have some gas. Let me make this slightly thicker. So you have a surface like this, in which inside this container, you have a gas. Okay. So through this, the net heat transfer is zero, let's say. And the net mass transfer in and out is also zero. There is no mass transfer, there is no heat transfer. So what do I call this wall as? What can I call this wall as? There is no heat transfer through it. So I can call it
Adiabatic.
adiabatic wall. I can call it as adiabatic wall. So basically, what this system is, it is a isolated system, meaning it is a closed system that does not interact with its surroundings, neither with mass nor with heat transfer. Okay. So you write an isolated, you keep drawing this kind of small figures, guys. An isolated system is a closed system, that does not interact with its surroundings. Full stop. For example, if the system consists of air in a sealed, rigid, insulated container, then the air may be considered as an isolated system, since it has no mass, work, or heat transfer with surroundings. With surroundings. Full stop. Now let's look at the open systems. Hope it is very clear. Isolated system and the closed systems. Okay. So this is an open system. This is a closed system. This one is a closed. This one is an open system. We'll look at the now. How do we look at the open systems? You write a control volume. CV. You write aka open system. Open system. So for open system, we use the control volume approach. So what is a control volume? A control volume is the particular volume chosen for study. Chosen for study. So unlike any system, closed system, matter may change within a control volume. Okay. So moreover, it does not need to be remain in the fixed shape also. It can change the fixed shape also, like moving control volume. Okay. Or it can change the location also. Means the control volume can move. So it may move, change size or shape. Okay. So you write unlike a closed system, matter may change within a control volume. So stop. Note that the control volume does not need to remain fixed in size or location. It may move or change size and shape. Okay. Move, you write. This one is move. For example, let me take one simple example. Let's make it like this. You can take it like this. So there is a mass inflow and outflow. You can have the heat transfer Q, or you can have the inflow also. So it can absorb the heat or it can reject the heat also, or it can release the heat. Okay. So this is basically your control volume. Okay. Hope you all noted this. Can I go ahead, guys?
Yes.
छोटे छोटे फिगर बनाते जाओ ऐसे.
Yes.
धीरे धीरे आपको लगेगा कि अरे कैसे क्या इंजन आगे सीख. Now let's look at the property. Okay. So there are two categories of properties. One is called extensive property and the other is called as intensive property. So you write an extensive property. आज मेरा थोड़ा हैंडराइटिंग खराब होगा, थोड़ा सा सुबह से बहुत लिख रहा हूँ, तो right. An extensive property is one that depends on the mass in the system. That depends on mass in the system. जैसे mass itself is an extensive property. Kinetic energy, that is half mv square, is an extensive property. So like that, any property that depends on the mass in the system, mass of the fluid present in the system, then it is called extensive property. So kinetic energy and mass are extensive properties. Right, next. An intensive property, you underline that, is one that is independent of the mass of the system, mass in the system. For example, temperature and pressure are intensive properties. They do not depend on mass. So in fact, how do we look at the properties like intensive and extensive properties? Let's see. One of the most simplest way is to whether the given property is intensive or extensive. Okay. Let's look at it. You write. So one of the best ways to divide the system into two parts, equal parts. Okay. And see how the property is affected. So you write an easy way to determine whether a property is extensive or intensive is to divide the system into two parts and see how the property is affected. So basically it is the shape also. So the volume also, we will see that. Let's take a case. Let's take one case. Okay. Let me fill this with some fluid. Let the volume of the gas in it be V. Let the mass be M. Let the pressure be P, temperature be T, density be rho. Now, if I divide this into two equal halves, okay, I'm dividing this into two equal parts. So when I divide this, what happens to the volume? What happened to the volume? Volume become halves. Okay. What happens to the mass? Becomes half. What happens to the pressure? Temperature? Density?
Same.
Same. So these are not affected by the mass and the volume. Hope this is clear. So these are called as intensive properties. Whereas volume depends on shape. So the shape is also a matter. This isn't. These two are, or instead of writing here, it will be good, nice if we write it here. These are extensive properties. We didn't talk about the volume in the previous definition. That's why I felt like you should know that it depends on the shape also. Fine. एक एक डिटेल पकड़ के बताऊंगा मैं. Can we go ahead, guys?
Yes.
Right. The state. अब state किसे बोलते हैं और process किसे बोलते हैं समझो. The state. So obviously state means what is the system's condition, okay, or the sufficient information about the particular system. If you have, that is what is called state of a system. Okay, the state of a system is the system's condition, or you can say configuration. As described by its properties. Okay, in sufficient detail, so that it is distinguishable, from other states. Okay, can somebody define process? So any state is represented by its properties, which are sufficient to differentiate it from the other state of it. Okay, what is a process?
The conversion of one state to another.
Correct. The transformation of system itself. Okay, what is your system? What you are considering for your study. For example, your system here is this gas. So this becomes your system. Okay, this is a closed system. In this one, this fluid becomes your system. Some case, the system would become the wall itself, or the table surface, or it could be anything, the room. Fine. So a process, right? A process is the transformation of a system from one state to another. From one state to another. You write a few common processes include, right, first one, isothermal process. What is the work, how we do the work transfer, everything we'll do step by step. Isothermal process. Okay. A process that occurs at constant temperature. Right? Next you write isobaric process. A process that occurs at constant pressure. Then you write isochoric or it is also called as isometric process. Some people don't know this name, that's why I'm listing this whole thing. Isochoric or isometric process. A process that happens in constant volume. Then you write adiabatic process. Adiabatic process. A process in which there is no heat transfer between the system and the surroundings. Okay, so you write that. You better write the whole sentence. Q equal to 0, you can write. Put a dash and write. Put a hyphen and write. A process in which there is no heat transfer. There is no heat transfer between the system and surroundings. Between the system and surroundings. Next, you write isentropic process. A process in which the entropy is constant. What is entropy? What is entropy?
Randomness.
It is no, not randomness. It is a measure of disorderness. Randomness is different. I can go randomly, but does not mean I'm having a disorder. Okay? It is a measure of disorderness. Now, one very important process, you write Cauchy process. You continue writing Cauchy equilibrium process. So it moves infinitesimally so slow that the system will remain very, very close to the equilibrium state at all times. Okay. So you write Cauchy equilibrium process is one where the process proceeds in such a manner that the system remains infinitesimally close to an equilibrium state at all times. At all times. Okay. Two more processes you write, then we'll move to the other thing. Because if I pick up word, I'll talk about it in detail. You write reversible process. Okay, is one in which the system is in a state of equilibrium, at all points in its path. So in a reversible process, the system, or in fact you can add and surroundings, can be restored exactly to their initial states. Okay, right, last one in the process, irreversible. Irreversible process is one where you won't be able to restore it back to the initial state. And it is not in a state of equilibrium at all points in its path. Okay, so irreversible process is one where the system is not in a state of equilibrium at all points in its path. Stop. Meaning the system and surroundings cannot be returned to their exact initial states in an irreversible process. So we can say that all natural processes are reversible or irreversible.
Irreversible.
So all natural processes are irreversible. For example, you can take several effects that cause irreversibility, which include viscosity effect, heat conduction, and mass diffusion. These are all examples of irreversible process. Okay. So you write process path. कोई process का path होता है ना? You write that process path is the series of states. एक छोटे छोटे स्टेट से डिवाइड कर सकते हो. Is the series of states that a system passes through during same process. Okay, that could be infinitesimally small change in the states. Okay, right. Next point you write. अब लिखते हैं cycle क्या होता है. So you combine sequence of processes, you will form the cycle. Okay, a cycle is a sequence of processes that begins and ends at the same state. So from where you start, there you have to come back by following several processes. So the whole thing is called as a cycle. Right, next. And EOS will write equation of chain and equation of state are very, very important aspects of thermodynamics. An equation of state is a relationship between properties of a particular substance or class of substances. So can you obtain an equation of state from thermodynamics? Can you obtain an equation of state, guys, from thermodynamics?
PV equals 10 sir.
Sorry? Can you
PV
repeat?
equals 10.
No, I'm asking from thermodynamics, can you derive it? Can you get that PV equals to MRT from thermodynamics? Remember that it cannot be obtained from thermodynamics. You are using it in thermodynamics. That does not mean from thermodynamics you got it. Okay, so you write EOS, equation of state, cannot be obtained from thermodynamics. But is obtained either from experimental measurements or from molecular model. Make a note. So there are two equations of state inside the equation of state itself. I'm not talking about equation of change. Okay. In the equation of state itself, there are two. One is called thermal equation of state. Another is called calorific equation of state. Okay. So you make a note. बहुत लोगों को ये भी नहीं पता होता. Write a note. There can be various types of equations of state. Equations of states. Example, for an ideal gas itself, you have two equations of state. Example, you write two equations of states for an ideal gas. For an ideal gas, include, right, number one, एक छोटी सी सब हेडिंग बना लो, make a sub heading, thermal equation of state. Which we very commonly use, in which you will have thermodynamic properties like pressure, temperature, density. Okay, it is nothing but the P equals to rho RT. What is the equation number we have, guys? I think 27, right? Hope we are running with 27.
Yes, sir.
Okay. Call this as equation number 27. Okay, what is this? Just now you said this, which is ideal gas law. PV equals to, oh, rho RT it is. I wrote RR. Okay, which is ideal gas law. Write the next one. It is called calorific equation of state. It is given by PU, that is the change in internal energy, is equals to CV dt. Bracket this. This is called calorific equation of state. Call this as equation number 28. So it describes, so you write, in bracket you write, which describes the relationship between internal energy and temperature. Close that bracket. Hope you all are through with this basic definitions of who is who. Write a heading, energy. Is it a physical quantity? Suppose there is an energy associated to some phenomena. Is it a physical quantity or not? Kinetic energy. Is it a physical quantity, guys? There's a mass, physical quantity, volume, physical quantity, temperature, you can sense it,
No, sir.
right? It is not a physical quantity. मतलब आप बोल नहीं सकते कि इसका physical quantity है पकड़ के कि इसका kinetic energy ऐसा है. Okay? Hope this is clear. So basically the energy that we say associated with some phenomena is not at all a physical quantity. Okay? It is just some number resulting from some formulas by having some physical measurable quantities. Okay, let's go ahead. So it will relate some measurable physical quantities which you can sense, like you can sense velocity, but you cannot sense directly the kinetic energy. समझ में आ रही बात? Hope you understand that. Velocity becomes the physically measurable quantity, whereas kinetic energy is not a physically measurable quantity. Hope you understand.
Yes, sir.
So it's some number basically. दिखेगा नहीं, लेकिन number होगा. Okay, so the energy. You're right. The energy. ऐसे एग्जाम्स आपको इंटरव्यूज में बहुत अच्छे से लेते हैं ये सब चीजें, ठीक है? They will take it seriously. How you understand this engineering and science. So you're right. The energy associated with some phenomenon is not a physical quantity, but is in fact just a number resulting from a formula containing physically measurable quantities related to that phenomenon. Example would be, one of the best example would be kinetic energy, half mv square. Okay, formula है ये बस. Hope it is clear. Physically आप इसको देख नहीं सकते ना, तो डायरेक्टली kinetic energy को सेंस कर सकते हो. You can sense the velocity. Can I go ahead, guys?
Yes, sir.
Basically, energy itself is not very useful quantity. Okay, experiments that of total energy of a system, that is sum of all the various energies, have resulted into a remarkable observations. You mentioned that energy by itself is not very useful quantity. ऐसे लग रहा है ना इसकी बेइज्जती कर रहा है, लेकिन ये बहुत यूजफुल है. ओके, when you take sum of all the energies together. However, experiments examining the total energy of a system, okay, you write, underline this, total energy of a system, that is the sum of all the various energies energies have resulted in a remarkable observation. In a remarkable observation. Right, next point. So, when the system does not interact with its surroundings, will the total energy change? Suppose the system is not interacting with the surroundings, will the total energy changes? No, it cannot change. Okay, so you note down that point. When the system does not interact with its surroundings, the total energy of the system remains constant. So the energy associated to the phenomena may change, okay, at the expense of the energy associated with some other phenomena also. Okay, we'll see that little later. You write kinetic energy. Write kinetic energy. Right. The energy will do lots of problems in thermodynamics and propulsion place, aircraft propulsion. ऐसा कोई न्यूमेरिकल जैसे आज मॉर्निंग वी टुक एंटायर रॉकेट प्रोपल्शन राइट, तो ऐसे ही पूरा एयरक्राफ्ट प्रोपल्शन भी कुछ नहीं छोड़ेंगे हम लोग. आई विल मेक श्योर दैट यू डू ईच एंड एवरी न्यूमेरिकल लाइक अ टाइम पास. ओके, राइट. द एनर्जी एसोसिएटेड with the macroscopic motion of a system relative to a coordinate system x, y, z or r, theta, z, like that, is known as the kinetic energy. K. So the kinetic energy is half m into v square. Bracket this. I believe this is 29. Call it as 29. Let me check. Yeah, it is 29. Okay, right, next, potential energy. Potential energy. Energy associated to system's ability to do work in an external force field, such as gravity, is called potential energy. Okay, so you write the energy associated with a system's ability to do work in an external force field such as gravity, field, is known as the potential energy. P. So this potential energy is denoted by mgz. Bracket this. Call this as equation number 30. So you can consider one small reference line or datum, what you can say. Take some typical mass M, which is located on which you are having the acceleration due to gravity G, okay, and which is located at a distance of Z. Okay, so you can write its potential energy as mgz. Whereas in space, we wrote slightly in a nice different fashion as minus gmm by r. You write next internal energy. In bracket, you write capital U. So this is like a combination of many subclasses. It is a combination, summation of internal energy is not just one. It is a combination of several different forms of energy. For example, it could be summation of sensible energy if it is there, latent energy if it is there, chemical energy if it is there, nuclear energy if it is there. So it is a combination of various subclasses. Okay, so you write the internal energy of a system is comprised of subclasses of energy which include you write number one, sensible energy. Sensible energy. Can you tell me what is this sensible energy means? Guys, anyone?
Energy is acting on a macroscopic level, which we can sense.
No. It is about the microscopic basically. This is the energy associated with the intermolecular translational, translations, rotations, vibrations, and all that. Okay. So you write this is the energy associated with the intermolecular translations, comma, rotations, translational, you write, comma, rotational and vibrational motions. Okay. So you write temperature is a measure of this type of internal energy. Full stop. The larger the temperature of a system, comma, the greater its sensible energy. The greater is its sensible energy. तो आप temperature sense कर सकते हो, okay, with the readings and all, but you cannot sense the exactly what is the intermolecular translations happening, rotations are happening, vibrations are happening. That the entire study is microscopic, which requires the study of kinetic theory of gases. Okay, hope you got the idea. Right, next, latent energy. Latent energy. So this is also a part of the internal energy. Can somebody say what is latent energy means?
Energy used to change its phase.
When a system changes its phase, the energy absorbed or released.
So what causes it? What causes it? Like solid to liquid or liquid to gas, there is some energy, right? So what causes this? It is the attraction between the molecules. So if the attraction between the molecules will be creating some sort of energy, because of which it will change the phase, like ice changing to water, water changing to vapors. Okay, so it's the force of attraction between the molecules. So you write, this is the energy. This is the energy associated with the attraction between molecules. Right? We concern ourselves with latent heat or latent energy most often when examining processes that involve a change of phase, that involve a change of phase. You underline this, a change of phase. Such as going from a solid to a liquid, or from a liquid to a gas, or vice versa also is you can take. So whenever there is a phase change, that is there because of the attraction between the molecules. So there is an energy associated to the attraction between the molecules. That energy is called as latent energy, which causes the change in phase. Right? Third one, chemical energy. So latent energy was between the molecules. Now, energy associated with the attraction between atoms is called chemical energy. So you write, this is the energy associated with the attraction between atoms. with the attraction between atoms. Right? Fourth one, nuclear energy is also a part of internal energy. Okay. So now in general, we used to say particle means set of molecules. Now we can choose within the atom also we can choose some further small particles. Okay. So you write nuclear energy, you write. This is the energy. This is the energy associated with the attraction between particles within an atom, such as attraction between protons and neutrons. It's called nuclear energy. So now we can sum up the total energy of a system as sum of these various types of energies. So all these summed up together, these four, okay? All these summed together, you can express that as the internal energy. Okay? So you write the total energy, of a system E is the sum of these various types of energies or energy, these various type of energy. So E is equals to U plus kinetic energy plus potential energy. Bracket this, call it as equation number 31. Hope you all reached till here, everybody. Okay. So right, are these extensive properties or intensive properties?
Extensive properties.
All these are extensive properties because all of them, they depend on the mass. Okay. Okay. So you write that all these are, right, all these are extensive properties. Full stop. In terms of specific quantities, that is, you take any extensive property, okay, that any one of these, and you do per unit mass. So that makes it specific quantity. We can write small e equals to small u plus v square by 2 plus gz. Or you write capital G. In place of P by M, you write capital G, which is gz. It's called conservative potential energy function. Okay, I'll mention that. You write where you can bracket this, call this as equation number 32. Call it as 32, right? Where small e is the specific total energy and U is the specific internal energy and V is the velocity magnitude and capital G is the, you write conservative It is a potential energy function given by G equals to small g z. Small g is the acceleration due to gravity, obviously. Write a heading, work. So you write, work is an energy interaction. You can say it is a way to transfer energy occurring at the boundary between a system and its surroundings. Stop. Thus, work is not a property of a system. Not a property of a system, but rather is associated with a process that the system is undergoing. That the system is undergoing. Right. First point you read. The work done on the system by its surroundings. This sign convention will follow always. Okay. By the surroundings depends on the path of the process, and it is taken as negative. So work done on the system will take it as negative. Work done by the system will take it as positive. I'll come to that. You write. Next you write power. You mention it with W dot. So work done per unit time is power. You write defined as the work done per unit time. Okay. So you define W dot equals to delta W by dt. Bracket this. Call this as equation number 33. So a small example would be small work done on the system can be written as force on the system which is creating the displacement small distance ds. Okay. Bracket this. Call it as equation number 34. And the corresponding power will be what? This is an example. What will be the corresponding power? W dot will be delta W on the system by dt. That is equal to F bar dot ds by dt. That is F bar into dot की बजाय into लिखना F bar, you better write dots. F bar dot V bar. Bracket this. Force into velocity is also power. Call this as 35. We did the entire performance based on that. Where what is V? V bar is velocity. Okay. Then the notation for total work required, you write the total work required is going the total work required in going from state 1 to state 2 is denoted by W12. That is 1 to 2 delta W is equals to 1 to 2 F bar dot ds. Bracket this. Call it as equation number 36. So you should note that the work done depends on path of the system. Now you write one question. A block with weight W is pushed on a frictional surface stop. The friction coefficient between the block and the surface is mu. Determine the amount of work done by the friction force on the block when moving the block from state 1 to state 2 using the paths shown. Okay. Draw one simple figure. Let this be a surface, and you have a block, frictional surface, on which you have a block like this. You have to move this block from here to this point. Okay. The distance that it has to move is, let's say, from here to here. Let the distance between these 2 points be L. And the path shown is state 1 to 2 you have to reach. The path shown is this. In the second scenario, you call this as A. And call this as B. So in this case, the path shown is like this. Okay. So the block must travel like this and then come to the state 2. Come on. Be quick. So this block is your system whose state is changing from 1 to 2. Come on, guys. Be quick. So what is delta W on block? F bar dot?
So mu
What is it? What is the
mu
force?
W into X, sir.
You better write X now because you are going only in X direction. Let this be the axis. So this will be mu W or minus mu W? Minus mu W into dx, right? Friction force acts in the opposite direction to your motion. So minus mu W into dx. So you write case A. What is the displacement? Total displacement is how much? In case A, L. So the work done on block will be 1 2 is 1 to 2 delta W is minus mu in W into L. So dx, if you integrate from 1 to 2, it is L. Whereas in case B, what is the total displacement? Sorry, total distance. Total distance. Yeah. Total distance is 3L. So you are doing more work on this. So work done on the block is 1 to 2 delta W is minus 3 mu WL. So even though the block starts and ends at the same location, the work done by the friction in the process is different. During the process is different since the paths are different. Hope this is clear. Therefore, work depends on path of the process. You always remember this. Okay. Let's look at one by one work. Let a bit gravitational work. That is basically potential energy. Fine. So let's take a typical reference point. So imagine I have a typical surface. Okay, this is an object. So my object of concern is this. Okay. So if I apply some external force on it, let's say a bar, and displace it from here, from this point to some other location at this point. Okay. Let's say I'm going to displace it like this, from here to some other point like this. Do it. Draw this, everybody. So I'm creating a change delta H, let's say, in the Z direction. Okay. There is this acceleration due to gravity G. So I'm moving from state 1 to 2. So how much is the work done on the system? My system is this rock or any mass. Or how much is the work done on the system? So state 1, I was at 0 and I changed the height to delta H in Z direction. That is F bar on system dot ds. Okay, so this is, you can write ds bar also to be more precise. You can write integral of 0 to delta h mg, let the unit vector in this direction be ez cap, be the unit vector in this direction, which is like this. So mg into ez cap dot delta h or dz you write into ez cap. Okay, ds bar is only in z direction. So if I define ds bar as ex cap plus dy ey cap plus dz ez cap, if motion is only in z direction, it would imply ds bar equals to dz ez cap. So I will be able to take the dot product of ez cap dot ez cap is mg dz. Integrating dz from 0 to delta h will produce mg into delta h. This is the work done on system for making it to come from state 1 to state 2. So what is basically the work done here? What is the work done? It is nothing but the change in potential energy. Call this as equation number 37. Call it as equation number 37. So you write the work done is equal to the change in potential energy of the system. Okay, note that the work on the surroundings is equal to, comma, but has the opposite sign. Of the work done on the system. So the usage of why I did this, I could have wrote simply mgh, but I want you to learn this. Okay, this is very important. Same thing I'll be doing it for kinetic energy also. So you write acceleration work. In bracket you write kinetic energy. Now let's take this mass. One second. Let's take this. Okay. And let me move it in this direction also. So I'm moving from state 1 to state 2. So I'm moving from state 1 to state 2. At state 1, let's say I apply a force F bar and I move this object from state 1 to state 2. At state 1, let's say it was having the velocity v1. Now at state 2, it is having some other velocity v2. Okay, so this is v1 and v2. Fine. So this is an object. This is an object with mass m you take. So you write the minimum the minimum work required to accelerate. I'll connect everything with the workplace. The minimum work required to accelerate an object with mass m from speed v1 to speed v2, that is W on system 1 2 is equals to 1 to 2 force that is acting on system dot ds. Make a note. That implies W on system 1 to 2 is equals to integral 1 to 2. What is the force? F bar. What is it? It is acting in which direction? I showed it in which direction, guys? X direction. So this is mass into acceleration in X direction. So let's say V is the velocity. So the M into A, that is dV by dt, rate of change of velocity in X direction. So this is your F bar dot ds can be written as what? V dt. ds can be written as V dt because V is ds by dt. In what direction? X direction. So you take the dot product of ex dot ex cap dot ex cap is 1. So you can write m into integral v1 to v2 v dv. Integrate this, you will be getting v square by 2. So substitute the limits, you will be getting half m into v2 square minus v1 square. So what is the work done on the system? 1 to 2, that is the change in kinetic energy. Bracket this. This is called acceleration work, which is called as the work is equal to change in the kinetic energy of the system. So you write the work is equal to the change in the kinetic energy of the system. Okay. Now let's move to the third form of the work, pressure work, which is very famous in thermo. Pressure work. Okay. Consider the work done by the expansion of a fluid. Let this be a gas or a liquid, that doesn't matter. Gas or liquid, close that bracket, in a piston cylinder arrangement. Piston cylinder as shown. Okay, so let me take piston. Draw this, everyone. That's obviously a moving boundary. And here is, you show here some direction X. Quick, if I apply a force to pull this piston, let's say the force applied is F. Let this be the force, and this is the fluid. This pink color is fluid. So the piston has moved by dx distance. So what is the work done on the system? Come on, you first draw that. Let the area of this be A and the pressure acting on the fluid be P. The pressure of the gas or fluid or liquid is P. The area of the piston is A. So the moving boundary has that elemental area A, let's say. Can I go ahead, guys?
Yes, sir.
So what is the work done on system 1 to 2 is what you will always write F bar on system dot ds. So how do we express this? 1 to 2, what is F bar? It is pressure into area. Acting in which direction? Ex cap. You're pulling the piston, right? So Ex cap, that is F bar. Dot, what is ds bar? Dx, Ex cap. Okay. So take the dot product 1 to 2. You'll get PA dx. Fine. What is A into dx? What is this? Area into length. What would be that? Bolo yaar.
Volume.
Volume.
Correct. So we write PdV 1 to 2. Bracket this. Call this as equation number 39. So you make one small note here, which I wanted to give before itself, I forgot. So you write W on the system is equals to minus of W on surrounding. W on SURR you write for the surrounding. Okay. You call this as equation number 40. So equal and opposite. So you write if we plot how the pressure changes with volume, what do we get? How the pressure changes with volume, what we get? We get a PV diagram. One of the most important diagrams in thermodynamics is PV diagram. So let's take one example. Let me take some typical example. Polytropic process. Let's say I'm having a polytropic process. PV power n equals to a constant. I'm drawing this. Draw one simple polytropic process. PV diagram. Okay. Let's say it was at state 1. Now it is reaching the state 2 by following this curve. Do it. So it was at state 1 at which you are having the pressure was P1, volume was V1. You were at state 1. Then you reach to state 2 at which the volume is P2 and the pressure is P2. So the path followed is this. And the area, we will need to compute that. So let's say I consider a small strip. On this axis, if I consider a strip, what this will be representing? dV.
dV.
Represented dV. Okay. So what is the area of this strip? What's the area of this strip?
PdV.
Area will be PdV. Fine. So here is our path. This is our path. Okay. So, and this is going to be our entire area which we have. So when I'm talking about this whole area, the area under this curve gives you what? What it gives you?
Work done.
Work done.
Work done. Okay. So I'm just highlighting this so that you understand it is the entire area under this curve. Okay. So my interest is that how do we look at if the path changes? Okay. Suppose this is one path. Okay. And what would be the other example of it? Let's say I reach the same point as in example 1. Now in example 2, if I reach the same point, so you make a figure like this. Draw this, everyone. So the area here, if you call it as A1 and you call this area as A2, both are different. Expressions of एक ही चीज होगी, but the curves are different. So you write W12 in A is clearly greater than W12 in B. So that is the area under PV curve 1 to 2. Will give you the work. Hope it is clear, everyone. Can I go ahead? कभी भी गलती नहीं चाहिए मुझे. अभी बोल रहा हूँ, आप लोग करोगे गलती इसमें, इसलिए मैं अच्छे से समझा भी दे रहा हूँ. बाद में देखना गलती करोगे आप लोग. Can I go ahead, guys?
Yes.
Right, D. Let's come to the electric work. Electric work. Right? Electrons moving across a system. Electrons moving across a system boundary can do work on a system. Since in an electric field, a force acts on an electron, full stop. Since in an electric field, a force acts on an electron, full stop. When n coulombs of electrons pass through a potential difference P, that is the voltage. In bracket you write voltage, comma. The electric work done on the system is, so you write W on system is NV. Bracket this, call it as equation number 41. Hope it is 41. Yeah. Interesting thing is power. The corresponding power is W dot on system is equals to V n dot. Okay. So that is V n dot. dN by dt is the current. VI. What is V? I into the resistance by Ohm's law. By Ohm's law, you can write V equals to IR. So you can write this as I square R, or you can write equal to V square by R also. That's up to you how you want to put it. Bracket this. Call this as equation number 42. Okay. Here I is the current and R is the resistance of the system. You can write where I is the current and V is the resistance of the system. Hope you all reached till here, everyone.
R is a resistance.
Oh, sorry, VI. R is. R is the resistance. Write E bit. Spring work. Spring work. Right. Now, let's examine the work required. The work required to compress a spring of stiffness K. So you can consider a small spring of stiffness K, and you can show it here. So let this be your system. The spring is your system. Consider that, let's say you are applying a force F on this system to compress this. So this is F. And this is the direction X. Draw that, everybody. So you are applying F in the opposite direction to X. You should be having, like friction was acting in the opposite direction. Now here, when you apply F, come on, in what direction you are applying? Opposite to the X, and it is equal to Kx. Fine. So how much you have to work? Work done on the system 1, 2 is equals to 1 to 2 F bar dot ds bar. What is it? You are going from x1 to, let's say, x2. Minus of kx into ex cap dot dx into ex cap. So you will be able to write minus k integral x1 to x2 x dx. So integrating that, you will get half k into x2 square by 2, half I already took. So x2 square minus x1 square, minus if you multiply, you will be able to write x1 square minus x2 square. That is equal to work done on system for 1 to 2. Bracket this. Call it as equation number 43. Hope you all reached till here. Everybody?
Yes, sir.
Write F. Shaft work. Shaft work. Right. Another method of transferring energy between a system and the surroundings is through shaft work. Draw a simple shaft and a small fan there. Make it, guys. Let this be omega, angular velocity, and let this be the torque T. Let's say the shaft is rotating with angular velocity omega. Can I go ahead, everyone?
Yes.
हमें प्रोपेलर और टर्बोफैन को रोटेट करना है, राइट? You will be requiring this. So the power, ये सब कुछ यूज करूंगा मैं आगे. The power acting on a system due to a rotating shaft is given by W dot on the system is equals to torque on the system times its angular velocity. That is, angular velocity can be written as 2 pi n by 60. Okay, so torque into 2 pi n by 60. Okay, n is the RPM. N is in RPM, revolutions per minute. So you bracket this. You should remember the power as 2 pi nt by 60. We all know that. बचपन से सुनते आ रहे हैं. अभी देखना, ये टॉर्क बाद में निकालना है हमें. एंगुलर वेलोसिटी भी यूज करेंगे. Okay, call this as equation number 44. Hope you all reached till here.
Yes, sir.
Omega is the T is the torque, and omega is angular velocity. मैं तुमको propulsion ऐसे पढ़ा रहा हूँ जैसे तुमने कभी पढ़ा ही नहीं. Okay, I'm assuming that you have not done anything. Can I go ahead? Hope you all are through. थोड़ा numericals करते हैं. Right, a gas in a piston assembly undergoes a polytropic expansion from an initial volume Vi equals to 0.1 meter cube and initial pressure Pi equals to 2 bar absolute. Okay, to a final volume of Vf. Remember, in all thermodynamic relations, you should use only absolute pressure, not the gauge pressure, not the vacuum pressure. Full stop. Determine the work the gas does on the piston for n equals to 1.5 and n equals to 1. देखते हैं कौन करता है. Where PV power n equals to a constant. So this is your piston and that's your gas. Come on guys. कैसे कर रहे हो? What is initial to final work? Integral VI to VF, right? PdV. ये आपका equation है. What is the power law you are following? PV power n equals to a constant. This is your second equation. So this would imply W initial to final equals to VI to VF. Okay, VI to VF. What will be P from this equation? CV power minus n. Agree? तो यहाँ पे लिखो आप CV power minus n dV. When you integrate this, you'll get W initial to final as दो इक्वेशंस आने चाहिए आपके पास. एक होगा C इंटू V पावर माइनस n प्लस 1 डिवाइड बाय माइनस n प्लस 1. This is only possible when you are having n not equal to 1. Whereas if n is equals to 1, तो क्या हो जाएगा ये? C by V, right? If n is equals to 1, what will happen to this equation? It will give you C integration of 1 by V dV will give you ln V. Vi to Vf when n is equals to 1. Make a note. करो ऐसे. Then you can put n equal to 1.5 for this part and use this equation. n equal to 1 के लिए ये यूज करोगे आप. 0 नहीं आएगा. अभी सब छोड़ो, अभी जो आपने रट रखा है अप्लाई करना शुरू करो. When n equals to 1.5. Okay, that means PV power 1.5 equal to C के लिए वर्क कर रहे हो. So what is it? What is the value of C? Come on. प्रेशर दिया हुआ था ना आपको 2 बार इनिशियली. वॉल्यूम भी दिया हुआ है. PI is, तो PI VI पावर 1.5 C होना चाहिए. That is 2 into 10 power 5 into VI is 0.1 to the power of 1.5. Give me value of C. C निकालो फटाफट. Come on guys. Sagar, give me value of C. Danish फिर से बोलो. 6.32 into 3, right? Very good. So WIF will become what? Use the n is not equal to 1 now. So you will use the equation C by 1 minus n. That is C is 6.32 into 10 power 3 by minus of 1.5 plus 1 into what is V final? How much is VF? कितना दिया था? 0.5 to the power of minus 0.5. Minus n plus 1 is minus 0.5. Minus initial is 0.1 to the power of minus 0.5. Calculate करो फटाफट. सौरभ चलो फटाफट कैलकुलेट करो. कोई फालतू आंसर नहीं देगा अभी. Come on guys, be quick. संदीप, come on. अश्रिता, संदीप, अभिषेक, अभिलाष, फटाफट आंसर्स देना शुरू करो. गिव मी द आंसर. मुरली, वर्टिका.
22
Is it 22.11?
22.095.
So you can approximately right. 22.2 में बोलो. 2.2
22.111 kilojoule.
correct. 2.211 into 10 power 4 लिख लेते हैं. राइट. न्यूटन मीटर होगा, वर्क है ये. ओके. या फिर किलो जूल भी लिख सकते हो. न्यूटन मीटर इज नथिंग बट जूल. सो 2.211 into 10 power 4 जूल्स. यहाँ तक तुम्हारा सौरभ करेक्ट था. राइट. अब आते हैं when n is equals to 1. When n equals to 1, meaning what is the power law here?
PV equal to
PV equal to C. तो क्या बदलेगा? C बदल जाएगा. So I will write PI VI equal to C. What was the pressure? 2 into 10 power 5 into 0.1 equals to C. So the coefficient जो होता है पावर लॉ का वो चेंज होता है. बहुत लोग उसको सेम लेके कर देते हैं, बस प्रोसेस को नहीं देखते. You have to see the process. Based on that, that C will change. So it will be coming as 2 into 10 power 4. So now you look at the integration that you did when n is equals to 1. Okay. So it is WIF is equals to C, that is 2 into 10 power 4 into ln of ln of 0.5 minus ln of 0.1. चलो फटाफट निकालो. सौरभ चलो बताओ आंसर. इसको भी इसके कंपैरेटिव में लिखना 10 पावर 4 में. गिव मी आंसर इन 10 पावर 4. कम ऑन वर्टिका.
So 3.21.
3.2188.
into 10 power 4. सौरभ जीरो हट के इतना बड़ा आ गया, उससे भी ज्यादा है ये. Is that clear? So the work done on the system when the process is PV equals to constant. ये कौन सा प्रोसेस है? n equal to 1 मतलब isothermal. Okay, it is a isothermal. So isothermal process में ज्यादा work required होगा, or the work produced by this, it is positive, right? So if the gas is moving isothermally, okay, it will do more work rather than the polytropically, like when the value of n is 1.5. Hope this is clear to everyone.
yes sir.
चलो अब एक और मस्त क्वेश्चन करते हैं. सारे क्वेश्चन में तुम्हें मस्त दूंगा, थोड़ी भी गड़बड़ करोगे गलती होगी आपसे. राइट. डिटरमिन ये क्वेश्चन करते हैं और आज छोड़ दूंगा मैं आपको क्लास. डिटरमिन द वर्क डन बाय द गैस on the piston shown below. As it expands quasi-statically from a volume of 0.02 meter cube to 0.04 meter cube. Given that the piston area is 0.01 meter square and the mass resting on the piston is 100 kg. Neglect weight of the piston. Full stop. Assume that the atmospheric pressure is 101 kPa. Absolute. Okay. Draw one simple figure. Let me take this. Take this. I don't want any mistake in this case. You show this G. You can ignore the mass of the or weight of the piston. Should not take more than 3 minutes. Come on. Deepesh Ranjan, are you there in class? Abhilash?
Yes.
Madhav?
Yes, sir.
Yes, sir.
ओके तुम में से कोई बोल रहे थे ना कि सर हमें साइकिल्स में बड़ा डर लगता है. तुम ये करते जाओ. साइकिल्स कब शुरू होंगे और कब खत्म हो जाएंगे आपको पता भी नहीं चलेगा. सीधे फिर ब्रिटन साइकिल पे हिट कर सकते हो फिर. कम ऑन गाइस, बी क्विक. प्रोसेस को समझ लो. इससे क्या कितना
1904
जूल किलो जूल यूनिट बोलो. 190
4
कितना
04 सर 1904
1904 जूल और किलो जूल.
जूल सर.
जूल्स. हु इज दिस?
केशव सर.
राम केशव.
ओके सर.
Others, come on, be quick. You give this answer and I'll wrap up the class.
Sir, 2020.196 जो
कौन है ये? शिवराम है क्या? 20
हाँ 20.196
जूल की किलो जूल.
सर जूल.
मैं ऐसे ही मजाक से पूछ रहा हूँ. गलत है. वैल्यू ही गलत है. जूल की जूल पे मैं पूछ रहा हूँ.
1982.2
कितना सागर?
1982.2 जूल.
0.2 जूल. गलत है सर.
3982.
Who is this?
Grisham.
Sorry, Grisham.
Yes, sir.
Very good, Grisham. 3982. क्या बात. Good job. तो बेसिक तुम्हारे फ्री बॉडी डायग्राम अच्छा है मतलब तुम्हारा, गुड वर्क. So if I take a piston and draw its FBD, always whenever this kind of things are given, you should try to draw the free body diagram. Okay, ये आपका PATM act कर रहा है, right? Acting on how much area? This is the force, right? From inside, you are having the pressure on the gas, right? कितना प्रेशर है? So this weight W is also acting on it. तो ये weight W को भी शो करो इधर. You should show the weight W. यहाँ से कुछ ऐसे मार्क कर देते हैं. W. That is mg. I would prefer writing it as mg. This is there because of this mass. Okay. इस मास की वजह से यहाँ पे फोर्स है mg, which is going to act on that surface. Okay. So how much is the pressure force the gas has to offer? P gas into A. So what is pressure? Force upon area. How much is the force? mg plus P atmosphere into A. Right? This much is the force acting on, right, downward, divided by the area. So I can get the pressure as PATM plus mg by A. Note that this is the pressure on the gas. So gas will develop this much pressure. So the work done would be V1 to V2 PdV. So you will be able to write this as PATM plus mg. This m is not the mass of the gas, so it won't contribute in the integral. So dV integration would give you V2 minus V1. Substitute everything. 101 into 10 power 3 plus 100 into 9.81 divided by area is given as 0.01 times of what is the volume? V2 कितना दिया है? 0.04 and V1 is 0.02. चलो फटाफट निकालो. ग्रीशम कितना बताया था? 3.982 ना किलो जूल. शाबाश. नेक्स्ट टाइम जब करोगे ऐसे प्रॉब्लम थोड़ा ध्यान देना. ओके.